Dear students, in this lecture, we are going to see one of the important impedance matching technique called quarter wave transformer. Now let us consider a transmission line whose characteristic impedance is Z0. This transmission line is terminated by a resistive load whose impedance is represented as ZR. So ZR is the load impedance, Z0 is the characteristic impedance. We all know that only if Z0 is equal to ZR, the line is said to be a matched transmission line, and in this case, all the power that is transmitted from the source to the load will be absorbed by the load itself. But in certain cases, whenever this Z0 is not equal to ZR, then the line is said to be a mismatched. The resistor, that is the load, is said to be mismatched, and in this case, a part of the incident power will be reflected back. So for this condition of Z0 not equal to ZR, we can say the line is a mismatched line and there will be reflection taking place. And this reflection, it is an undesirable one and it has to be avoided in any transmission line. Now, if we want to avoid this reflection taking place from the load to the source, one way to avoid this is by inserting a matching network in between the transmission line and the load. In between this transmission line and the load, we have to insert a matching network. The purpose of the matching network is it will match the load impedance ZR to be equal to the characteristic impedance Z0. When these two becomes equal, then there won't be any reflection taking place from the load to the source. That is the purpose of this matching network. And one simple matching network that can be used is called quarter wave transformer. This is the simplest matching network. And how this is constructed is you can make use of a transmission line of length equal to lambda by 4. That is why it is named as quarter wave. The length of this transmission line is equal to lambda by 4. Now this short piece of a transmission line is going to act as a matching network. We have connected a short piece of a transmission line between the actually existing transmission line and the load. The purpose of this transmission line, whose length is equal to lambda by 4, is to match the load impedance ZR to that of the characteristic impedance of the transmission line Z0. Okay. Now, we are going to find the characteristic impedance Z0 of this short piece of a transmission line of length lambda by 4. This is called as the matching network. We all know that the input impedance, that is the source impedance of any transmission line, is given by R0 into ZR plus J R0 tan beta S by R0 plus J ZR tan beta S. This is the actual input impedance of a transmission line, of any transmission line. Now, in this case, we have inserted a piece of a transmission line whose length is equal to lambda by 4. And we all also know that beta is 2 pi by lambda. So beta is 2 pi by lambda and the length of the transmission line S is equal to lambda by 4. So we can find beta S by substituting these two values. Now beta S value will be equal to pi by 2. Let us substitute this value of beta S in the above equation. So if I substitute beta S as pi by 2 here, this becomes tan pi by 2. It becomes tan pi by 2. We all know that tan 90 is infinity. So directly if I substitute pi by 2 in the existing expression itself, this entire input impedance becomes infinite. In order to avoid this, let us rewrite the same expression ZS by taking tan beta is common. So it becomes ZR by tan beta is plus J R naught divided by ZR by it is R naught by tan beta is plus J ZR. We all know that beta s is pi by 2. So it becomes R naught into ZR divided by tan pi by 2 plus J R naught divided by R naught by tan pi by 2 plus J ZR. That value of tan pi by 2 is infinity. ZR by infinity becomes 0. R naught by infinity becomes 0. So the first term in both the numerator and the denominator will become 0. This is 0 and this also becomes 0. So we will get ZS as R naught into J R naught divided by J ZR. J gets cancelled. So this becomes R naught square divided by ZR. So ZS is R naught square divided by ZR. R naught is nothing but the characteristic impedance of the short piece of a transmission line that we have inserted. So R naught can also be represented as Z naught. We can write the same expression as Z naught is equal to R naught is equal to root of ZS into ZR. So R naught square is ZS into ZR. R naught is root of ZS into ZR. So now this is the characteristic impedance of the short piece of a transmission line of length lambda by 4 that we have inserted between the source impedance and the load impedance. From this we can say that if we insert a short piece of a transmission line of length equal to lambda by 4, whose characteristic impedance Z0 is equal to root of ZS into ZR, then we can ensure that the source impedance will be made equal to that of the load impedance. The transmission line is said to be a matched transmission line, and this will avoid reflection. In other ways, we can say this will ensure maximum power transfer from the source to the load. That is what is given here. The two resistive impedances can be matched. The resistive impedances are ZS and ZR. It can be matched by a section of a transmission line, by this section of a transmission line, which is quarter wavelength long. It should be of length lambda by 4, quarter wavelength long, and has a characteristic impedance equal to the geometric mean of two resistances. So if we insert a transmission line of length lambda by 4, whose characteristic impedance Z0 is equal to the square root of ZS and ZR, then we can say these two resistances, which is ZS and ZR, will be will become matched. And this will avoid reflection. That's all about quarter wave impedance matching. Thank you.